we are reporting our activities, everything. The most notable activity that we did last year was on electric vehicle, and that was done with help of Priyesh Chauhan, who is our technical activity chair, and it was done organized in his campus of IIT RAM in physical mode. When we were deciding about this workshop, we were thinking of doing it, whether we should do it in physical or hybrid, or even in this mode of online mode. But we took a brave decision to do it in physical mode, and it has got a tremendous response from the audience. Because of Dr. Panda's location in Singapore, we decided for this to be organized in hybrid. So there are, I believe, that there are some delegates who are right now sitting in person in NIT Surat, this hall, which Mullah is facing. And there are many, around 50, 60 delegates or participants who are online also. So I am quite happy seeing this response of the delegates, and without taking much time. Let me introduce my XCOM before closing this. So Dr. Mullah is vice chair of this chapter. He will take over from me next year. He should have taken over this year only, but he is he will take over next year. We have two lady volunteers also on our XCOM, Priyanka Sharma and Manisha Shukla. And they are also contributing a lot to this chapter. Priyesh is, as I told you, Priyesh is our technical activity chair, and Dr. Amit Ved, who is in Marwari University, Rajkot, is our secretary come treasurer also. So we have a good bandwidth and a good team of volunteers to look after all the activities. So with this, I again welcome Dr. Panda for this engaging title of the talk, to deliver his talk. So I hand over to that volunteer student who is anchoring this event. So thank you very much.
Thank you, sir. Now I would like to invite Dr. Suresh to introduce our speaker, Dr. Panda.
Thank you, Ishan. It's my pleasure to introduce today's speaker, Dr. S.K. Panda, who received a Bachelor of Engineering degree from the South Gujarat University, India in 1983, and MTech degree from Indian Institute of Technology, Banaras Hindu University, Varanasi, India in 1987, and PhD degree from the University of Cambridge, UK in 1991, all in electrical engineering. He was the recipient of Cambridge Nehru Scholarship and the M.T. Mayer Graduate Scholarship during his PhD study, 1987 to 1991. Since 1992, he has held a faculty position in the Department of Electrical and Computer Engineering at the National University of Singapore, and is currently serving as an associate professor and director of Power and Energy Research Area. Professor Panda has published more than 450 peer-reviewed research papers, co-authored one book, and contributed to several book chapters, holds 6 patents, and is the co-founder of 3 startup companies. His research interests include high-performance control of motor drives and power electronic converters, condition monitoring and predictive maintenance, building energy efficiency enhancement, etc. He is serving as an associate editor of IEEE Transactions on Power Electronics, IEEE Transactions on Industrial Applications, IEEE Transactions on Energy Conversion, IEEE Axis, and IEEE Journal of Emerging and Cellular Topics in Power Electronics. He is the chair of IEEE PELS Technical Committee TS12, Energy Axis, and Off-Grid Systems. In 2020, Professor Panda was elevated to IEEE Fellow for his contribution to iterative learning control of motor drives. With this, please join me in welcome Professor Panda. Now I hand over the session to Professor Panda and request him to start this talk. Sir, welcome, sir.
Thank you. Excuse me. Thank you very much for inviting me. Is my screen still visible to you people? Hello? Is the screen visible to everybody, right?
Yes, sir. Yes, sir.
Yes, visible.
Okay. Thank you. Thank you very much for inviting me for this particular session, which I'm giving it online. My sincere apology. First of all, Dr. Mulla invited me to give this talk along with Dr. Priyesh Chauhan from Ahmedabad. He was my research fellow. So I accepted their invitation quite some time back. But at that point of time, I didn't have the intention to, rather, I didn't plan to visit Surat because I'm planning for visiting Gujarat sometime later and give talks at multiple places. But because of the PELS Day celebration, they invited me, and I said that, okay, I'll accept it. But I didn't know that in between there was some development. I'm actually physically in India, not in Singapore now. I'm speaking to you from a hotel in Chennai because in an hour's time or 1.5 hour time, I'll be giving a lecture at the Sai Ram College of Engineering in Chennai. Their student branch have got a best student branch chapter award, and they invited me to give a lecture. It was a last moment arrangement, so I'm here. Sorry that I'm not physically present in Surat, but I'm still closer to Surat from Chennai than from Singapore. Okay, and it's an honor for me being an alumni of the SVNIT. I always thought I must come and give a talk for SVNIT. At that time, we call it SVREC, Regional Engineering College, when I joined in 1979. Okay, I'm not going to go details of that. So let me start my presentation. I'm putting into the presentation mode. I cannot see you people when I'm presenting it here because I'm not very used to this Google Meet. Most of the time we use at NUS Zoom meeting or MS Team meeting. So I had some difficulty in logging into the Google account because I didn't have a Google account. My NUS doesn't allow to have a Google account. So I had to call my daughter to give her Google account and password so that I could join in at the last moment. Sorry about that trouble. So the talk I'll be giving today, it'll be on the microgrid part of it. So the introduction to the Power Electronic Society, I'll be doing it briefly. Then there is an introduction to the responsive grid. This is about the electric grid back in Singapore and what are the activities being done in Singapore. Plug and play autonomous microgrid system, that's the topic.
Prof, sorry to interrupt, but I think you have placed it in presentation mode, but the slides are not moving. So,
How about now? Not moving?
not yet. Maybe you unshare and share it again. Yeah, now it is moving, but not the presentation mode.
How about now it is moving?
Yes, Prof.
Okay, then I don't go to the presentation mode in order not to create more confusion.
Okay.
You people can see everything, right?
Yes, Prof.
Just give me a minute. Okay, when I come back to this part, I don't see my own slide. So I will go back. Sorry guys, give me I'd stop and I present it again. and I cannot see my own slide. Okay, give me a minute. I shouldn't have touched that one. So let's stop sharing. Hold on a minute. So are you able to see it now?
Not yet, Prof.
How about now? No, not yet.
No, not yet.
Yeah, give me a minute. How about now?
Yes, it's visible now.
Is the slide moving now?
Yes, Prof.
Okay, let's go with this thing. All right, thank you. I'll be giving a brief introduction to the Power Electronics Society because they are the financial sponsor for this particular talk, and introduce you the various Power Electronics Society, the president and the membership list. Then I'll go to the introduction to responsive grid. That is the grid that we have in Singapore. We call it as a grid 2.0 for research point of view. Then the final topic will be the plug and play autonomous microgrid that is chosen by Dr. Mullah to give the talk. So I hope I cannot see all of you now, but I hope majority of you are IEEE members and you know what IEEE is. It's the Institute of Electrical and Electronics Engineers, and the IEEE is divided into 39 different societies under IEEE. So Power Electronics Society is one of the 39 societies of the IEEE, where people dealing with power electronics domain are member of the society. Okay? And we deal with power electronics as a sustainable energy technology for the betterment of the energy uses in this world. So IEEE is a, IEEE PELS is a not-for-profit organization society within the IEEE, and it is not that old compared to our sister societies. Can you see my cursor moving? Is my cursor moving? Are you able to see?
Yes.
Yes, sir.
Yes, sir.
Fine. So the Power Electronics Society was founded only in 1987, 87 to 22, about 36 years old. And we have worldwide membership. 10,000 is a little bit outdated. We have close to about 12,000 members. And India is one of the promising country in the region 10 where the Power Electronics Society membership growth can be expanded even further. I would just like to highlight that in Gujarat, you have only one power electronics chapter. I wanted to have a power electronics chapter, multiple power electronics chapter within Gujarat, be one in Ahmedabad, one in Baroda, one in Surat, like that, so that people can attend the talk at various places and not able to move from one place to another place just to attend a seminar. I will plan with Dr. Mullah, who will be taking over as the chairmanship next year in this regard. These are our PELS Administrative Committee members. The present PELS president is Brad Lehman. He's from Northeastern University in Boston in USA. The immediate past president is Liu Chen Chang. He is from Canada, but he has retired now, emeritus professor. And you must be knowing Freddie Blabjerk, who is known as the father of the power electronics technology, we call it. So he is the senior past president. Okay. And the presidency goes for a rotation of 2 years. These are the administrative vice president committee member. I'm not going to go details of it, but I myself come under vice president membership, which is Mark De Hong from the China. The university is Zhejiang University. They do quite a bit of work in power electronics domain. The question is why one should be an IEEE member. It's a professional society. To be a member of the IEEE, it's an honor for you. And once you are become an IEEE member, to get the benefits of the power electronics domain, you need to be a power electronics society member as well. So by being a member of the society, you could get all this publication in the digital form, not in the, you can get it in the printed form at a cost, but with the bare minimum $10 USD, a member can get all these magazine in the digital. Now, you would be paying, I'll show you the membership fees. The membership fees have been dropped or reduced drastically over the year. And from 20.
Sir, your mic is mute.
Sorry, somehow the mic got mute. I don't know why. Okay, I go back. Am I audible now? Everything is okay?
Yes, sir.
Sorry about that. Okay. Now, yeah, by being a member, if you attend any of the conference, there is a registration fee. So that registration fee is usually about $400 to $800. But once you are a member, you could get a discount about 50 to 75 US dollar, and you pay a membership fee of only about $10. So the student member will pay about $5. So all the students, whoever are attending this meeting, they can remember that by being a student member, you are paying a fee of just $5, but by attending one of the conferences, you could save about $50. So that's the benefit of being a member, and you have multiple resource-centered digital media where you can get all the access in the archive thing. On the right-hand side, you see the technical committees. There are 12 different technical committees. The very bottom one, energy access and off-grid system, that one I'm chairing it at the moment. This is basically linked to the Sustainable Development Goal of the United Nations, SDG 7, where we provide energy access to the poorest people in the remote part of the world. So there are 12 different technical committees. This is free of cost. Anybody who is an IEEE member or student member can join this committee, free of cost. We have networking benefits for the membership in all the conferences. Applied Power Electronics Conference, ECCE in North America, in Asia, in Europe. And I'm glad to inform you that ECCE Asia, which normally runs between Japan, Korea, and China, the fourth year, now it started in 2017, it was in Taiwan. And 2021, I did it as an organizing chair in Singapore. That was the COVID time, so it was a virtual conference. Now, this year in May, we had the conference in Jeju Island in South Korea. But 2 years down the road, 2025, ECC Asia will be brought into India. Looking at the importance of India, the PELS senior member committee at committee have decided to bring it to India, and it will be held in Bangalore by the Bangalore chapter from with Professor Kaushik Basu from IISc Bangalore. So these are all these PELS society-sponsored conferences, and there are many other conferences which are technically co-sponsored by PELS or financially co-sponsored by PELS. For example, the National Power Electronics Conference, which will be held in Guwahati in a few months' time, that is sponsored by the PELS Society. And PEDES, which was held last year, December in Jaipur, that is also sponsored by the PELS Society. So members can participate in the technical committee, conference committee, the chapter committee. We have a women in engineering. I don't know what percentage of the student in Surat are girls. In our days, you could just hardly count. In my cohort, probably there were 3 students in the electrical and a couple of more in the civil engineering, and total less than 10. I'm not sure out of 150 or so, but nowadays the ratio of the women must be much higher. So IEEE promotes for gender equality. So we promote women in engineering. So they have their own thing, and the picture that you see at the bottom, this is women in engineering. And all these things are young professional meeting in one of the society level conferences. These are the distinguished lecture program, and each distinguished lecture like this I'm giving as a distinguished lecture. So we are shortlisted by the society worldwide for about 10 people in the distinguished lecture program, and one can continue for a second round of 2 years. So I was already selected for 2022-23, so I am here, and I'm again selected for 20. Yeah, there is a mistake here. This is 21-22, this should be 22-23, something like that way. So just like your Dr. Mulla has invited me to be a part, or rather to give a distinguished lecture, we have a Google form. Somebody can click on that one on the website and request for giving a distinguished lecture, either virtually or physically. These are all the student activities we do. There are various competition, and because of the shortage of time, I'm not going through the details. This is standards we develop by IEEE. So this is mainly for industry people where they come into contribute in developing the standards. So Smart Grid Standard 1541 by IEEE, that is related to the Smart Grid, which IEEE developed. The other important thing is the IEEE Transportation Electrification Community. So as you know, we are making a transportation sector to completely change from internal combustion engine to electric vehicle. So it is not only electric vehicle on the road, it is also electric vehicle on sea, like the bottom picture you see, the harbor craft, and even in the air, these 2 pictures that you see. So land, sea, and air, all the transportation will be getting changed into full electric mode. And that is the Power Electronics Society is the home society for IEEE Transportation Electrification. And the other 3 societies, Power and Energy Society, Industry Application Society, and Industrial Electronics Society, join us in this mission. So fuel your career and future, your future basically. Join the IEEE if you haven't joined it, and once you join IEEE, then you be a member of the PELS Society today, and get connected to the community. And basically, the Power Electronics Society disseminate the knowledge in the sustainable development using power electronics technology in the industry. So these are our administrative officers at the IEEE PELS Society. So you can now join the essential membership. I'm not sure whether you are aware or not. This year beginning, the essential membership, the US $25 has been reduced to bare minimum $10. This is for full year for full member, rather members and senior member and higher. For the student, we have reduced the membership fee to $5. You know, if you buy a McDonald's burger, that cost about US $5 in the US, in Singapore also it cost about 7 Singapore dollar. So in India, I think it costs about 400 rupees to 500 rupees. So you just sacrifice one McDonald's burger and you can take up a student membership, and then you will be rich with all the information in the power electronics domain. This is the list of things what PELS can offer you. And one of the competition, Empower a Billion Lives, EBL. This is the competition we have done, Power Electronics Society has done 2 times. 2019 is the first EBL 1. 2023 we did the EBL 2. And the next one will be in 2025. And there are 12 technical committees. So that gives the background about the Power Electronics Society. I'm not stopping here for any questions because the time is short. So I need to move on and just wait until the end where you can have any question. I'll be answering it. Now I'm zooming in. By the way, can I get a feedback? Is my voice clear? I'm not muted. You can see the slides moving. Is everything okay?
Yes, all okay, Prof.
No. All right, let's move on. So, responsive grids of the future energy systems. Now, as I told you, the present grid is called grid 1.0. Now we have grid 2.0. So what is the difference between the grid 2.0 and 1.0? In a grid 1.0, you have the conventional power plant and they are connected to the distribution network. But in grid 2.0, you can see a black color square box here, 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 all these places. So these are called ECC. You cannot read it here, but this is referring to ECC, Energy Control Center. So any electrical energy from the generation side to the transmission and distribution side has to go through a energy control center that can regulate the flow of energy, and it can make it bidirectional power flow as well. So besides having the conventional grid, you will have a distributed renewable energy sources, like in this case, wind turbine. I'm in Chennai. I see so many wind turbines around Tamil Nadu state. I am sure in Gujarat also it will be there. It must be there. Then you can have solar panels distributed way. On this side, we have the industrial load and the commercial load. All of these entities are connected to the future microgrid through the energy control centers. And the role and responsibility of the ECC is to do active power flow control, compensation it provides, VAR compensation, harmonic compensation. It controls the DC link voltage that integrates the renewable energy sources as well as the storage into the grid, microgrid control for islanding or grid connected mode, and information sharing between the microgrid and the rest of the newly developed microgrid. So within the ECC, there is something called like a solid state transformer. Our normal transformers are line frequency transformer 50 or 60 hertz, but solid state transformer operate at a much higher frequency. So isolation can be provided using a high frequency transformer and power electronic switches. So the size of the transformer reduces by a factor of 10. then you don't need bulky transformer, and in the substation, you could have a high frequency transformer to provide the isolation. They are also known as a power electronic transformer or smart transformer, depending on what type of structure or topology they have. This is the challenge for mitigating the carbon emission in Grid 2.0. The red graph that you see here, on y-axis, we have the total electricity generation or consumption in gigawatt hour. X-axis is the time in years. It is only for 1 decade it has been shown here. So the red line curve that you see, excuse me, that is increasing linearly. So the energy consumption is increasing linearly. And the green graph that you see, which is here, the grid emission factor, and this is measured in kg of CO2 emitted into the environment per kilowatt hour of energy usage. While the energy consumption is increasing, how come the grid emission factor is dropping? The reason for that is we are using over the year and replacing the crude carbon-rich fossil fuel like coal and other things, oil. We are replacing it with the cleanest form of the fossil fuel, that is the natural gas. So 97% of the electricity in Singapore are generated using natural gas. And we get the natural gas through the pipe connection from Malaysia, from Indonesia, and we convert the natural gas into electricity in various power plants. And therefore, we have managed to reduce the grid emission factor. But the question is, this blue color line that you see, horizontal line, even if you use 100% natural gas, the grid emission factor can be theoretically reduced to 0.41. It is now 0.42. But we cannot reduce beyond 0.41, and that's the factual barrier. So the question comes to mind is, how am I going to reduce the energy grid emission factor while increasing the energy consumption? That can only be done if we rely on not natural gas, but portion of the power generation is using renewable energy. And in Singapore, because very close to the equator, wind speed is less than 3 or 4 meters per second. So wind energy, we cannot take it renewable, or we cannot tap on it. But we could tap on solar. So photovoltaic solar power generation has been the way to go forward in Grid 2.0. And the government of Singapore has already taken a drastic step. All the government buildings in Singapore have rooftop solar panel, and we produce at this moment about 500 megawatt peak solar power. That is not sufficient. Our total power consumption is about 8 gigawatt. So 500 megawatt peak is a very small percentage. But by 2030, the government has planned to increase the solar power from 500 megawatt peak by 4 times to 2 gigawatt peak. So 2 out of 8 gigawatt will be roughly about 25%. So we can reduce the grid emission factor by bringing in renewable energy. The other way to reduce the grid emission factor is by tapping on renewable energy, not in Singapore, but from abroad. So we have invested and signed a contract in Laos PDR, one of the ASEAN countries, where they have a significant amount of hydropower generation, and their power demand is not that high. So using the ASEAN grid, we will be bringing 25% of the renewable energy from other countries into Singapore. That's how we hope to get about 50% from renewable, and we could reduce the grid emission factor dramatically. This is, I'm sorry, this is a animated thing, but I don't want to go to the presentation mode because that will cause other problem. So I'm not showing you, but this is animated picture. This is conventional grid. your generation, centralized power generation. This is the load center. Power flows from the generator to the load in a unidirectional way. That's the present system. In the future system, we are not going to throw away the conventional generation. We retain it as it is, but we develop responsive, distributed local generation. You can have renewable one, renewable two, energy storage devices, all interconnected in a distributed way all over the island, and they become the microgrid. And that is the topic of interest. This load has to be responsive. That means we could divide the load into critical and non-critical load. Those critical load must be supplied. When the power generation is in trouble, some generator has tripped, then the generation capacity has gone down, then actively we could do demand response and curtail some of the non-critical load demand and reduce the load demand so that we could match the generation with the load. So the load has to be responsive, the microgrid has to be responsive, the generation must be responsive. And if we do all these things, we could achieve grid 2.0. This is a distributed multiple places, the thing. So grid 2.0 must be able to optimize energy savings, reduce carbon footprint, maintain grid stability, improve self-sustainability, accommodate further structural changes to the development of the grid. All these things cannot be done by human being, so it has to be managed by intelligent machines. So that's the future of the power grid and real-time power flow management control in the grid 2.0. Singapore, there are a lot of high-rise building. So building, commercial and residential building consume about 30% of the total electricity we generate. A building, this you see the color is brown. A brown color building means it's not good. It's consuming significant amount of fossil fuel and emitting CO2 to the environment. And there is a high dependency on the utility grid. If the utility grid fails, the building will be blackout. So this is a consumer, but in future, or it is already taking place in Singapore, the buildings are becoming green under the Green Building Innovation Program, where they have rooftop solar panel. They can have a wind turbine in other parts of the world. They can have energy storage devices. So sometimes the building can produce enough power that they have surplus. In that case, they can sell back power to the grid. You see, here it is unidirectional power flow. Here it is bidirectional. Sometimes building can consume power from the grid, and some other times, if they have sufficient, self-sufficient and net positive, they can throw back or transfer power to the utility grid. Then the building becomes a prosumer. Prosumer is the term coined by the power engineers. Producer plus consumer. So building can be a consumer sometime, building can be a producer sometime. So we say it is a prosumer. Guys, everything okay?
Yes, Prof. We can hear you and we can see the slides.
Thank you. So I need the feedback because I cannot see your photographs and other things.
Participants are asking questions in chat box, but we'll take at the end of the presentation.
Let me finish this one, then I can unshare. Then I can see everybody's face, then I can answer. It will be much easier.
Sure, Prof.
Okay. Now, animation part, you cannot see it. So this is the conventional grid. So the question is the grid really necessary? So conventional grid, yes, the green is the grid part there. The grid of the near future, we are moving from here to here. Then we have distributed generation, energy storage, renewable energy, flexible demand, and these are all microgrid. But the grid is still there. This will be happening in the next 10 years in Singapore. But beyond 2030 or beyond 2050, we may be arriving here. So this is the grid of the future. Now, what's the difference between grid of the near future and grid of the future? Can you identify what is missing in the grid of the future? This G block is no longer there. That means conventional grid. If you are building a new city, just like in Andhra Pradesh, they were building, Singapore was involved to build the new city. That one, you may not have a grid there at all. Then all are microgrid and all are distributed and they are interconnected. Then we may not need the grid at all. Just give me a minute. I need some water. Just 1 second. Wow. All right. So we anticipate that in future it might be like this. And the younger generation, people like you, I'm already retiring. So you will be telling me in the future whether future grid doesn't need the grid at all, basically. It's just like you look at the landline when I was young, left India about 40 years back. Getting a landline when I was young, you have to wait for 5 years. Nowadays, after 40, 50 years, do you think anybody is going for landline? No. If it is there, it is there. But nobody will be applying for a landline because every individual member has a mobile phone. So we leapfrog from landline-based telephone to mobile phone. So the future grid, you leapfrog from the grid to a distribution grid without the main power generation grid. That's what I mean here. G means grid means the power generation, centralized power generation. We don't need it and we will be here. This is electricity consumption in Singapore. This is the Singapore Island. NUS is somewhere here, southwest. So we have solar in all the government buildings and things like that. Even if we put the whole island with solar panel, we cannot produce 8 gigawatt of power because we don't have that much of land. So from the land, we are now gone to the reservoir. So somewhere here, we have all the reservoir. So reservoir, there are floating solar panels on the water. So we produce electricity from there. Still, it is not sufficient. So now we have gone Singapore Islands all over here, the sea, within the international law, the part of the sea, we are having floating solar panel to produce electricity there and connect back to the grid. So this is the future. We are looking at it. We'll be going by 2030 from 500 megawatt peak to 2 gigawatt peak. We'll have more than 200 megawatt of energy storage device by 2025. By 2030, 60,000 EV chargers will be installed. And by 2040, all the vehicle in Singapore will be EV. There'll be no internal combustion engine. And you guys all did electrical engineering, so this is the best time to be an electrical engineer. You tell your counterpart mechanical people that their jobs are on the number, means they are going to be replaced by electrical engineer designing EV. I'm just making a joke there. Okay, mechanical engineer you still need. So Singapore sustainability target, basically you do demand response, you go renewable energy supply side. We are counting for the transportation sector hydrogen, but it is yet to be resolved how you provide hydrogen in the vehicle. Then the planning paradigm 2, I cannot read it very clearly here. So all these things are linked to the grid. Okay. Building consume 30% of the energy. So multiple projects we have funded by the Building Construction Authority. They call it as 2030 program is 80 by 80 by 80. 80% of the buildings will be green by 2030. 80% of the new development of the buildings will be SLE. SLE stands for super low energy. And I'm telling you, if you Google within NUS, we have a School of Design and Environment under the College of Design and Engineering, SDE 3 and 4. These two buildings are net positive within the campus. And we are developing a microgrid as a part of the living lab of the NUS Kentridge campus. Prius has been there, so he must know. Part of the NUS campus will be microgrid. And then 80% is on the energy efficiency improvement. Air conditioning consumes almost 70% of the energy within the building. Lighting consumes another 20%. So 70 plus 20, 90%. If the electrical engineers play a part to reduce the energy consumption, that is what 80% of the energy efficiency improvement that can be done. There are different schemes the government provides for people to tap on it. That gives the background about Singapore Grid 2.0. Now I'm coming to the actual topic, which is the microgrid system. By the way, just give me a minute. Yeah. The microgrid system that we have. All right, sorry, I wanted to say that this part of the work was done by one of my PhD student. His name is Souvik Dasgupta, came from Bengal. He graduated sometime back in 2012 or so. So this part of the work is already 10 years old when he did his PhD. So one part of his work I'll be presenting, plug and play microgrid system. That's what has been chosen as the seminar topic. And even if it is 10 years back we have done, it is yet to be implemented at scale. So the NUS microgrid we are developing now might have some features of it. So what is a microgrid? It is grid connected. So your utility grid at the top, then you have a step down transformer. So this may be at about 22 kV. Then you step it down to 415 volts. So this is the three-phase 415 volt line. Some loads, heavy loads might be at 22 kV. And this is the static transfer switch. You may not be able to see or read. It is STS, static transfer switch. So basically it is a switch to make the microgrid grid connected or grid islanded. So that's there. Then we come, this red box that you see here, that is one of the DG1, distributed generation 1. This is distributed generator 2, and this is distributed generator 3. So how different distributed generator can be connected to the microgrid, that's the topic of interest. And how the microgrid research is done is basically high bandwidth active and reactive power flow control, total harmonic distortion control, load voltage regulation, all these things are done. If it is grid connected, then the grid maintains the voltage. So we don't do load voltage regulation. But if it is grid islanded, which is what the next topic will be, then load voltage regulation has to be done. So if it is grid connected, then the inverter so this is renewable energy source, there is a storage, there is an inverter. And this renewable energy source, which is DC, is inverted back into AC and fed into the system. So this inverter operates in current control voltage source inverter mode, CCVSI, and injects a certain amount of active and reactive power into the grid. Okay. But if it has to maintain the voltage, then one of the inverter will be operating in not current controlled, but voltage controlled voltage source inverter. So depending on the usage, grid forming or grid following inverter. Now we are coming to the main topic. I should be finishing soon. Another 10 minutes. So let me explain. This is the common bus or the microgrid, the red color line that you see. We did not implement in the field, but we implemented this in the lab environment. Okay. So I have a DG1, which is the diesel generator based one. With a switch, we can connect or we can disconnect. I have renewable energy source DG2, which can be connected, disconnected. I have an energy storage, which can act as a source or act as a load. And I have a photovoltaic source, DG3. Then I have two types of load. One is the residential load and one is the commercial load, like a data center. So Singapore has lots of data center. Your Tatas, Meta, Amazon, all these people, they built data center in Singapore to protect their data, basically. So different distributed generator or load or the energy storage elements can be plugged in or plugged out. So the whole idea, plug and play, just like in a computer, through the USB port, I can connect a mouse, I can connect a microphone, speaker, or a music system. I can plug it in, plug it out. So I don't stop the computer operation. As soon as through the USB port something is connected, they will do the handshaking and then they will transfer information, be it data, be it storage, be it a music system. Same way, in a power grid or rather microgrid, can we plug in a distributed generating source or can we plug out without disrupting the operation? Can I plug in a load? Can I plug out a load? That's the whole rationale. So all these things can be plugged in or out without any mutual communications. So basically, we are saying that there is no wireless communication between these sources or the centralized controller. And each distributed generators or the loads are placed far away, maybe sometimes a few kilometers to tens of kilometers. So there is no communication channel directly available. Okay. If the problem statement clear, then I will explain details of it. So these things, I'm not going to read it out. The slides will be shared to you. So in the proposed system, the main energy source, which is called as a master source, is capable of supplying the load, the total load of the microgrid, along with stabilizing the grid voltage. So the master energy source, be it DG1 or 2 or 3, maintains the grid voltage. Is that clear? I'll explain this in the diagram in a while. Different renewable energy sources, DG2 or 3, they act as slave. So they operate based on the master. So when they are acting as a slave, to reduce the active power usage of the master, they can inject a certain amount of real power P or imaginary power Q into the system to reduce the burden on the master. A secondary energy generating source, which is also connected to the same grid, which is acting as a slave, but that is pre-decided that if the master fails, one of the slave then becomes the master. On the backup, he is there. So this other generator, which takes over as a master source, just give me a minute. Yeah, I think that people calling from the other lab, yeah. Sorry, what I was saying, I forgot. Yeah. So this one of the slave has been designated to run as a master when the master fails. So it will take it over as a master source. And I say that we do not have a communication link. Yes, we do not have a direct communication link. either wirelessly between the different sources, but we have a signature voltage identification method. You can call it like a power line communication indirectly, but when the master is alive and maintaining the grid voltage, there is a signal in that voltage that can be extracted by the slave, and then they know the master is alive. They don't need to worry about the grid voltage. They will just inject a certain amount of P and Q. So without any extra communication link, but this grid voltage is monitored by the load and the source generating sources slaves, and they can operate accordingly. Arbitrarily, you can switch on or switch off the loads or the secondary energy storage, and we use a controller called Spatial Repetitive Control. Spatial Repetitive Control is something similar to an integral control, but you don't do integral control unlike you do it in a normal PI controller. Every sample point to sample point, you do integral control. Spatial repetitive control is more for steady state. So we do integral control cycle by cycle. So we store the information of one electrical cycle, 0 to 2 pi or 360 degree, and store it in the memory, use it in the next control cycle, basically. Neither the grid voltage frequency fluctuates nor the energy storage element needs further information of the load current, blah, blah, blah. So we don't do droop control, basically. And laboratory prototype of the autonomous microgrid system is developed, implemented, and experimental results will be presented in the next. I hope that part is clear to you. So this is the microgrid. It is a single phase system. I have DG3, DG2, and DG1. So DG1, I'm assuming, is based on the diesel generator. It's producing AC to DC converter. Then you have an inverter to give you the voltage of the grid. V load, VL. Okay. This is renewable energy source. So it injects PG, and this is another source which injects PB, active power into the system. I have two load 1 and load 2. One of these sources is a energy storage device, so that can act as a source or it can act as a load. That's the whole idea. Are you all clear? So I have three sources. One, DG1 acts as a master, DG2 and 3 acts as a slave. Okay, and 3 is probably energy storage device. So power flow is bidirectional. I'm going a little bit deeper now. So we modeled DG1 operates in the voltage control voltage source inverter. So this is the master and maintains the load voltage VL. VL is across here. Yeah. DG2 and 3 operate as slaves and operate in current control voltage source inverter. So this is DG2, DG3, and they inject a certain amount of current ID into the system. And this is the load, which is variable. And this is the transmission line impedance that is there. And this L and C is basically a filter to filter out the high frequency of the inverter output. Okay. Load, I said there are two types of load. One is a resistive load, RS, and one is a data center load, which is nonlinear. So nonlinear load is represented by a diode bridge rectifier with a capacitor. So the current I1 is highly nonlinear in nature. I2 is linear, and the total combination is the load current. The signature voltage that I said, so VL plus V signature is monitored at the grid level. we have designed a sharp notch filter, 8th order Butterworth IR filter, and the frequency of this signature, rather, the magnitude of the signature is 1% of the peak value of the load voltage, grid voltage, and the frequency is chosen to be 11 hertz. I also don't remember now, but there is a scientific reason why 11 hertz was chosen. So this notch filter filters out the line voltage, line frequency, grid voltage, and comes out or extracts the signature voltage. Then there is a level detector. If this is present, the state is high. If it is not present, the state will be low. It's basically a digital signature. So when it goes low, the other loads know that the master has failed. And these are so this is the line voltage that you see. There is some interruption because of the 11 hertz frequency. So there is some disruption there if we zoom into it, but otherwise you don't see it because this magnitude is only 1%. Okay. So this picture is at 10% of VL. This is 5%, and this is 1%, something like that. Now this is the experimental test bed. We use a DSpace-based controller. Let me understand it. Yeah, this is DG1, DG2, DG3, passive load, resistive load 1, nonlinear load 2. And all the parameters are all given. By the way, this is published in the IEEE transaction. I cannot recall power electronics or industrial electronics. You can Google it and you get the details of it. So I'll give you 3 scenarios. I'm running out of time now. Case 1, sudden plugging in of the nonlinear load. DG1 is acting as a voltage control voltage source inverter and maintaining the grid voltage. Load 1 is already on. Load 1 means this load. So the passive load is already on and this nonlinear load is switched on at a particular time. So DG1 supplies about 53 watt with IS1 to the linear load and maintains VL. So at the beginning of the cycle or the waveform, zoomed view is here. This is the voltage VL of the grid and this is the current. Remember, this is coming from the source 1. This is minus IS1. The voltage and the current are out of phase, but actually it is in phase. So this is negative of the current. So negative of the current means this will be at the bottom current and voltage is at the bottom. So basically they are in phase. Okay, unity power factor operation. And this is feeding a linear resistive load. So the current is sinusoidal, voltage is sinusoidal. All okay? Guys, respond. Okay, no. Hello?
Sir, yes, sir.
Everything okay? You are understanding,
Yes, sir.
right?
Everything is okay, sir.
Okay. Now, Mike, you mute it. Yeah. At this point, we do the transition. So until now, only the resistive load was there, which is zoomed view is shown here. During the transition, I put in the load 2, which is the nonlinear load, suddenly switched on. And DG2 and 3 are off. Okay? So DG1 is sufficient to maintain the load. So this zoomed view is shown in the middle part. This is the voltage. This is the current, IS1, minus IS1. So as soon as I put the load 2 on, which is a rectifier load, the transient part you could see here. The current builds up or increases because the second load is connected on the top of the load 1. Now, the second load is nonlinear. So the zoomed view in the steady state is shown here. The grid voltage is still the same as before. But this load current is a combination of resistive and rectifier load current. So the load current is highly nonlinear. You can see it, right? You compare with this linear load, it is sinusoidal. Nonlinear load, it has significant amount of harmonics. So basically, load 2 I have plugged in without disrupting the system, and everything is stable. Clear? Next. This is case 2. Sudden change in DG2 current reversal. So DG2 is a energy storage device. There is a current reversal. So DG2 earlier was acting as a source. So it was supplying load, active power. But now I changed halfway through. The DG2 battery, instead of sourcing power, it is consuming power. That means it acts as a load and gets charged. So that charge current will come from DG1. Have I made myself clear? It is getting a little bit complex now.
Yes, sir. Yes.
DG1 still acting as a voltage control voltage source inverter with loads connected and active power flow of DG2, which is current control voltage source inverter, suddenly reversed. So you will see that DG2 current will change from positive to negative. So like battery was discharging earlier, now it will get charged. But in this diagram, I am showing you DG1 parameter only. So before the transition, the load voltage, this is the IS1, and this is IDC1. IDC1 is positive with respect to the ground. That means the source 1 is supplying active power to the load. Here we do the transition. So you see the source current 1 now increases compared to this, and the DC level current IDC1 compared to this, here it has gone up because the DG2 is acting as a load now. So you see IDC1 at steady state has a higher average voltage because it was not only supplying to other load, but also it is now supplying to DG2. So DG2 is connected to feed active power 70 watt to loads to reduce the power from DG1. This is at the beginning. And DG2 provides a peak current of 2 ampere. IS1 provides only harmonic current to the nonlinear load. So now I go to DG2. So DG1 parameters are clear. So here we are seeing DG2 during that transition, where we change DG2 power flow. While earlier DG2 was supplying power, now it will act as a load and consuming power. So this is DG2 parameter. This is IDC2. So DC link 2 current is positive at this point. Positive means DC link current 2 means DG2 was supplying active power to the load. We make the transition here at this point. So this positive current, which the battery was supplying to the load, now reverses and your current becomes negative, IDC2. So you see IDC2, this is 0 and it has some ripple, but the average current is negative. That means the source 2 is now consuming power. This is on the DC link side. Here you see IS2 and VL both are positive. That means power by DG2 was transferred to the load. But after doing the transition here, load voltage still remains the same, but the current is 180-degree out of phase with respect to the voltage in AC side. IS2 is 180-degree out of phase with VL. So VL times IS2 is the negative power. So the source 2 is consuming power. And in the DC side, power is flowing into the battery. So DC2 current is negative. Here it was positive, here it is negative. And this is the transient operation. So DG2 power command is reversed to minus 70 watt, resulting in distortion of the AC voltage. And blah, 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 that I have explained. You could read it through. Case 3. Sudden shutdown of the master. So the master fails. So DG1 is switched off. And we make sure that DG3 slave has already been pre-decided will act as a master in the case master fails. So DG3 takes charge from current control voltage source inverter to become voltage control voltage source inverter and maintains the grid voltage. And then you have DG1 and 2 parameter. So this is DG1. At this point,
Sorry to interrupt. Can you share the presentation again? It somehow turned off. I'm not able to see the slides.
Darshan, it is actually visible. You only need to pin it. You just click on the pin icon, then it will be visible.
I continue.
Prof, I can see the slide. I'm not sure. So how about the other participants? Is it visible?
Yes, sir, we can see.
Okay, I resume.
Yeah, I can see now. Okay. Thank you.
Yeah, but I cannot see. Yeah, you can see there. Let me go back to my presentation. Yeah. Okay. Now, okay, let me get rid of this Google Chrome. Yeah. So at this point, we switched off DG1. So IS1 current becomes 0 because the master has failed. And zoomed view of that you see here. Earlier, IS1 was supplying the nonlinear current, but then it becomes switched off. So the DG1 has been disconnected. Clear? Now, when DG1 has been disconnected, nobody is maintaining the grid voltage. And that's why the zoomed view you see here, VL starts to bulge up or the voltage increases because nobody is maintaining the voltage. And DG3 doesn't realize that there is a problem. So DG3 is still operating at a current control voltage source inverter. So during this period at the middle, nobody is maintaining the grid voltage. After a gap of about 50 millisecond or so, or something like that, 500 millisecond, the DG3 V signature is detected and DG3 operates as a master and maintains VL back to normal. So during this period, the grid voltage is increasing. At this point, when DG3 realizes the signature voltage is no longer there, that means the master has failed. So DG3 changes its role from current control voltage source inverter to the voltage control voltage source inverter. And then you see the voltage is again brought back to the nominal value. You see here? And the corresponding IS2 current. So Come on, guy. Just give me a minute. Hello? Yeah, you wait. I'm in a meeting. I finish the meeting. I'll come in about 5-10 minutes time. You wait there at the lobby. Thank you. Bye. Bye. Hey guys, the other call has come. I need to go. All right. So DG1 is switched off. DG3 takes over the charge of the voltage control, voltage source inverter, and DG3 parameters are all shown. So I skip this slide. So to conclude, development of the plug and play type of autonomous smart microgrid systems, we have done it, implemented in the real time in the lab experiment, of course at low power level, but mind it, control algorithm remains the same, whether you do at 100 watt or 100 megawatt. So same control algorithm can work for higher power transfer as well. High performance control for current and voltage quality is maintained using this special repetitive control. Arbitrary integration of the renewable energy sources, diesel generator, and other genetic systems with the bus voltage stabilization capability has been demonstrated. Sudden change in the load. Initially, it was linear load, then suddenly we put in the second nonlinear load. So sudden change in the loading condition while maintaining bus voltage is maintained. Automatic changeover to energy storage element in the case of excess active power. So the energy storage initially was discharging, and at a given point of time, you had excess power in the system. So the energy storage, rather than discharging, becomes a load and starts to charge. So excess surplus power is diverted to the storage element. Power line communication between multiple generators to maintain the stability. So the signature analysis has been done at 11 hertz signal, and we demonstrated that all the activities of a plug and play microgrid can be done. Thank you very much for your attention. This is my contact number. So with that, I stop my presentation and come back to the discussion part, any Q&A if you have. I'm stopping the presentation slide now. Okay. Now we are free to have any chat or any discussion that you have. I'll have about 5 or 6 minutes before 5 minutes. Now it is 10:55. Okay, go ahead.
Okay, so there are a couple of questions posted in the chat box. So first one is from Manisha Shukla. What are the types and examples of responsive load and how it is planned to manage through DSM?
You speak a little slowly.
What are the types and examples of responsive load and how is it planned to manage? Question mark through DSM.
Yeah, responsive load are, you divide the load into two types. One is called critical, one is called non-critical. Now the user defines this, like for example, a data center load will be a critical load that has to be maintained all the time. You cannot expect a failure in the data center load. But the air conditioning system in the building can be considered as a non-critical load. So if you have a power crunch, you continue to supply power to the data center load, but you reduce the power to the air conditioning system. So for 10 minutes or 15 minutes, you switch off the air conditioning, people will feel uncomfortable, but it is not like life and death scenario. I hope that answers the question. And it is done through the intelligent control, that which load will be disconnected through a switch, non-critical load, and critical load will continue to get the power. Next question, please.
So the next question is from Shiva Prasad. What is the major challenge in the floating solar system?
No, there is no challenge except that you have to design the structure where the solar panels will be mounted in the floating living lab. And how do you anchor it to the seabed? That's the challenge. That's more of a civil engineering or mechanical problem. But electrical side, I don't, I haven't experienced myself. I'm not involved in the project, but I don't see any other type of problem there from electrical point of view.
Okay, so moving on to the next question from Darshan Pandit. How an inverter can control grid voltage? Does it function as DVR or similar topology?
How does inverter control the grid voltage? Is that the question you're saying?
Yes, sir.
Yeah. So inverter has two type of role. It is grid forming or grid following. So in the case of the islanded microgrid, like the one I presented, the diesel generator 1 inverter, not diesel generator, DG1, distributed generator 1 inverter is in the grid forming mode. So your reference is the load voltage, which is perfectly sinusoidal, and the inverter ensures that the voltage output from the inverter is following the reference sinusoidal voltage. So there it is maintaining the grid, the voltage magnitude, as well as the frequency.
Okay, so now moving on to the last part, I would like to call upon Dr. Mullah for a memento presentation and vote of thanks.
Sorry, there was a question from Mona Lisa. What is green hydrogen? What is the status of green hydrogen?
Yeah, good morning, sir. Thank you.
Green hydrogen, there are again three different types. One is called, one is green, one is blue, and one is something else. There are three different types of hydrogen.
Yes.
Hydrogen can be produced, but the problem is transportation of the hydrogen. It is flammable. So in Singapore, the government or the civil defense, SCDF, Singapore Civil Defense Authority, they don't allow transportation of the hydrogen tanks inside the tunnel, because if it explodes, the tunnel will explode and a lot of disaster will happen. So transporting hydrogen from point A to point B is yet to be resolved. But using electrolyzer, taking water and splitting it to hydrogen or oxygen, that can be done. And use fuel cell to power loads. Yeah. Sorry, guys, I have to stop here. Let's conclude the thing.
Okay, sir. Now let's conclude. I would like to call upon Dr. Mullah for a memento presentation and vote of thanks.
Thank you very much, sir, for the useful talk, and our apology for whatever connectivity and Google Meet problem we faced. So on behalf of organizing committee, we would like to offer you a small memento, which we will share with you whenever you'll be in Gujarat, or maybe we'll be posting you. So thank you very much, sir, for this wonderful.
Thank you very much.
Lecture.
Yeah, it is good to see the photograph, and I still recall Ichanath temple used to be there. It's still there, I guess. And whenever we get tired of studying, we go to the Ichanath temple, especially just before the exam, to pray God. So we do well. So I'm sorry that I couldn't physically come over, but Priyesh,
I also
inviting me to come to Gujarat. I'm here in Chennai, unfortunately. Otherwise, I could have.
Our SVNIT.
Yeah. Thank you very much. And how many people we have online? Oh, there are about 55 people. Okay, that's good. And look, physically, how many people are there? Dr. Mullah, how many people are there in your hall?
Prof, I think you are not audible to Dr. Mullah itself. So he and his part of speech.
Yeah, I think his voice is cutting down. Okay, thank you very much. But yes, I will plan to come
Thank
to
you, sir.
Gujarat
Thank you very much.
for about a week in Ahmedabad, in Baroda, and Surat physically. But I just need to figure it out a right time to do that one. And it's a pleasure to or honor to talk to you know my institute SVNIT, which I intend to do for a long time. So maybe it wasn't the right time. So today was the right time. We could talk at least virtually. Next time it will be physical. Thank you very much.
We look
and
forward
appreciate
for
it.
you to visit, sir.
Thank you. Bye-bye.
Bye-bye.
All right, I cut up now. Thank you. Bye.
Goodbye, Prof.
Bye.
So, dear participant, thank you very much for your participation. And we thank SVNIT and Electrical Department for all infrastructure support. And feedback form is shared by Ehsan in the chat box. And sorry for the inconvenience in execution. Sir was not having Google access, that was not known to us. So over to you, Ehsan.
Okay, thank you all for joining, and we appreciate your time. Please don't forget to submit the feedback form, and the link is available in the chat box. Thank you. I would request everyone to please turn on their camera for a group photograph. Can everyone please turn on their camera? Okay, thank you, everyone.
Hello. Hello.
Yes, Manisha, madam, you are audible.
Priyesha, yeah, Priyesha, if you can share this feedback link in the email also. Maybe if we disconnect from the meeting, it will be lost.
Definitely, we will share via individual email as well.
Yeah, and it was a nice session. So whenever Panda sir is visiting Gujarat, let us know. We will organize this session at our campus also.
Sure. In fact, he has shown willingness to visit various places like Vadodara, Ahmedabad, and
Yeah, I have heard that. Yeah. So maybe we can plan out some professional activity under the IEEE banner. Manisha ma'am is already talking to related to this. So maybe we will work out offline.
Sure. Yeah.
Okay. Thank you. Thank you. Mullah sir, thank you so much.
Thank you, Mullah sir, and
Thank you,
all
madam.
organizing team.
Thank you all. Thank you.
Thank you.
Thank you. Goodbye.
Bye.
Have a good day, everyone.
Chalo, Ehsan. Recording stop.
केम छो मुल्ला सर